I have the pleasure of introducing the speaker today is Dr. Dutta. He got his PhD at the University of Arkansas, spent about a year there, and then went to Harris-Stowe University, which is in St. Louis. And this is an opportunity that came out of what originated from I guess it was a graduate fair last summer that I attended that Harris-Stowe sponsored. It was for undergraduate students that they had there who were looking for graduate programs to go to. It was STEM related. And when I was there, I had the opportunity to meet some of the administrators there, and one of those was Dr. DiCarlo. And he contacted me and said, hey, you know, we'd really like to try to establish a seminar series. We can start small and hopefully build it bigger. And so I solicited to several colleges to see if anyone was interested. And fortunately, one of the math faculty was interested, and we actually got faculty from the Department of History who went to Harris-Stowe about a month ago.
Yeah.
And then so today we're honored with the presence of Dr. Dutta. And so that's how this all started, and I really hope that we can start to grow this, you know, and kind of maybe more formalize a seminar series between Harris-Stowe and SIU, and develop collaborations between the faculty and student exchanges, you know, whatever evolves from that. So thank you for taking the time to come down and speak to us.
Thank you. Thank you, Lucas. So thank you for providing me with this opportunity to present my research here at Southern Illinois. I would like to thank Dr. Sullivan for giving a talk at Harris-Stowe, which I unfortunately missed. And thank you. And I was guessing, what if he doesn't come to my talk?
No.
So what he did. So thank you. So I'm going to talk about the area I work on is composition operator. In general, we call this area it's a mixture of operator theory, function analysis, and then complex analysis of one variable. And there's a name for it. It's called geometric function theory or function theory. So this is an active research field. There's some big result. Some people proved it before even I get into this field. and so this operator has there's some areas where they have some good application of this operator. Some mathematicians, they're trying to solve invariant subspace problem and all that, and then in dynamical system, applied mathematician, they use this operator to solve differential equations. So which I don't know much about. I know the pure math side of it. I study this operator, I study the properties of this operator, like is it bounded, is it compact, is it close range, things like that. So today I'm going to talk about close range composition operators. Before that, I'll introduce you to the operator and the kind of spaces it works on, the general one, the one we work on mostly. And I'm going to talk about boundedness of this operator. If I have time in the end, and I'll talk about the compactness as well, because there's some really big result in the compactness of this operator, and that's the side of this operator being studied extensively. Right now we study the closeness because there's so much work has been done on compactness of this operator. Okay, so first of all, okay, so this is my setting here. So I'm going to work on the unit disk, which is denoted by D there, and then this boundary, which is the unit circle. And H of D is the space of all analytic functions on the unit disk. functions which are differentiable on the unit disk at any point. N denotes the Levitt measure, a normalized Levitt measure on the unit circle, which is normalized in the sense the probability measure. And then you have A is the normalized Levitt area measure on the disk. So I know my talk is about any Banach space, any general space, but I always like to start with the Hardy space because it's a easy start and simple to understand, and it's one of the very fascinating space, even though it's the basic one. Still, the things work really nice in this case. So, so Hardy space are defined as this. These are functions, which are analytic functions on the disk, for which this is the norm on the space. Functions which this integral is finite, and then you have for p even as infinity, for which you have bounded analytic functions, functions which are bounded on the in the disk, and you have and this is the norm, the supreme norm on those functions. So these are Banach space, complete metric spaces. Right? Now, one good thing about these spaces is that so we saw the norm is given in terms of the boundary values, where r goes to 1. But the good thing is that this boundary limit, these values exist almost everywhere on the unit circle. So we can just take the boundary value of it and represent this norm in terms of the boundary values, the functions. So here's the composition operator. This is defined. So if we take any analytic self map of the disk to itself, we define a composition operator on HP on the hard disk space or any other space as a composition of F with phi, and it takes the function from the HP to HP. The first thing, whenever we have an operator like this, we care about is it bounded.
Really strong bound there.
Yeah,
I don't know, is this a positive thing or negative thing?
There may have been a power blink or something to the cord, then it reboots and it says, oh, I need to do updates, and
May not be bounded enough.
It's plugging in, yeah, it's plugging in. The power seems to be okay. Yeah, it's restarted. That's good news.
if need be, we have chalk.
Oh, yeah.
Yeah.
I'd say, since we have some few seconds here, most of this setting, and the good thing about this talk is, which I personally like, that even if you don't, so some of the results here, obviously, I'll use terms that you may or may not understand like quickly, because there's some information, you may need more background. But things like the result that I have does not actually, has very less connection with the work that has been done. So I'm going to go with the history of closed-range composition operator, where their results were for each species, someone proved what it takes to be close range. And how do you define close range in each spaces? Like you go to Hardy space, you go to other Banach space in general. But my question is about if it's close range on this space, is it close range to a subspace of it? So which is it's like implication of close rangeness between spaces. So I did not have to go through the hard work of proving this close range in each spaces, which some other people, mathematicians, who have already done it for me. So this is an observation that was made by some researchers, some implication as a corollary to the air in those spaces, but never been investigated in general, what it takes to be from any general bounded space to any general bounded space, what it takes to be close range. Does it imply close ranges?
It's astounding that Windows dominates the market. It's just biggest quirky paradox.
So mathematician needs to work on it.
Yeah. That was the Unabomber. Well, not.
This never happens at Harris Stowe, does it?
Oh no, it happens.
Great.
Happens.
Just okay.
Fake, yeah.
This happens in my stat lab class. I have to run from my computer to the screen. And sometimes you just guess it, you see the time, then you apply, then you do some predictions. So, it's a few seconds. I should go and touch it before it goes out again.
We can maximize it. It's hard.
We upgraded your software so it no longer works.
Copy to the desktop. Is it?
Yeah.
And
We can maximize
Full
it.
screen, yeah.
Full screen. Hopefully it will work.
Yeah, yeah.
Nobody's reading now.
HV spaces, this is the norm on the HV space. Okay, so there's a nice result there that's done in I don't know which year, probably 1900s. So Little or maybe before that, Little subordination principle, which says that composition operator on Hardy spaces is bounded. And plain and simple bounded, and not only on and this is the theorem, and this is the subordination principle we use it to show that it's bounded on, and this is the bound on that. There's a similar result in the Bargmann space, which is next. So Hardy space we defined in terms of the boundary limit, right? Into the Lebesgue measure on the unit circle. And there's a Bargmann space which you define this way. It's a weighted Bargmann space. So you have this nice weight here with respect to the area measure on the disk. So this is a bigger space than the Hardy space, and its composition operator, which is a result of Littlewood's theorem that I just talked about, it's also bounded on this space as well. There's a slight change here. That was 1 over p. This is 2 over p. So it's nice Hardy and Bargmann space, but that's not the case in other spaces. And there's some complicated results in spaces like Dirichlet space that we'll talk about later, where it's not, boundedness does not come as a gift. Alright, so we want to talk about closed range composition operator. What does closed range means? It's a range is a closed subspace of the image space. So this composition operator, it goes from so HP to HP or Borgman to Borgman spaces, right? Whatever Borgman spaces. So it's saying is the image is closed subspace of the other space. Now, so that's the general definition for any operator to be closed range, right? But if you're a bounded operator, and which is one-to-one, there's another nice property composition operator has. This one-to-one, as long as it's non-constant. So it's bounded and one-to-one on any Banach space analytic functions on D has closed range if and only if it's bounded below. Okay, so it's bounded above and it's one-to-one, which is it's a general theorem in function analysis or in operator theory, which says that you have closed range if you're bounded below. So we're going to use this one. So these are the Banach spaces that I was talking about. We already talked about these two, Hardy space, Borgman space. Then there's this classic Dirichlet space, which is given by this norm. This kind of looks similar, right? Some of them were connected in a way. There are identities in the field where this norm can be connected or they can be represented like the norms in the other spaces. And there's this base of type spaces which pretty much encompasses most of these spaces. So this is more general. This is more general. And we're going to see implication of closed rangeness from the bigger space to smaller space, or bigger subspaces to smaller subspaces within these general spaces. So this is the work that has been done. The first one was Seymour, Thompson, and Ogun in '74. That's the first condition for CP to be closed range on the Hardy spaces. Okay, so they came out this nice condition there is closed range if it's the Radon-Nikodym derivative of this particular measure on the which depends on the property of the map, analytic self-map phi on the boundary. So we call this induced measure or pullback measure, and he's saying this this derivative, this d mu phi or dm is essentially bounded away from zero. And so this result, I don't know, it looks really complicated. So one thing about I don't know, I probably missed it. That the good thing about this operator is that most of its properties of these results can be explained in terms of the behavior of the function phi. It has nothing to do with f. It's only the image of the phi. So that's why we are not dealing with abstract operator theory here or something. We're just dealing with a function too. We only care about the properties of phi on the boundary or on the disk, what it does. So this condition, this closed range, is this measure in terms of the boundary behavior of the phi. Now he posed a question: can you talk about closed rangeness in terms of the behavior of the map of phi on the disk in general, not just on the boundary? So this that's 20 years later. Nina Zorgowska came up with the condition, giving necessary and sufficient condition for closed rangeness on Hardy space or HP spaces in terms of sets like this. Now, we're satisfied with this because that's the first a nice result in terms of the map of the in terms of the image of the phi on the disk. But sets like this is hard to imagine, hard to picture. So this is called Neverland accounting function, which tells you the affinity of phi, like how it assumes the value on the unit disk. And so you can see this is some kind of like a weighted criteria here that we use. Take the pre-image of phi and count their multiplicities and all that, and see how phi takes all these values with all the multiplicities. So, and this condition is called reverse correlation condition, which was invented by Dan Loken, who never worked on the composition operator theory, but did work on Topli's operator, and he came up with this condition, and right after he came up with the condition, this paper came out, and it's like, that's it, that's what we need. Sets like this, sets that's inside the disk at the same time close to a boundary, so. But this is not what I need for my for the results I have. But these are the hard work they did in order to prove there's close range on these spaces for this particular necessary and sufficient condition. So these are other Banach spaces on Bergman space, these are general Bergman spaces. So instead of sets like with Neverland accounting function, they use sets like this, which is easier to understand. Don't have to deal with any sum, anything. But still, there are a lot of gravity details here. To picture in this set, it does take a, like a lot more understanding of this little detail of these maps. This is another. This is for those base-up type spaces, those general object spaces, and that's for another base-up space, which is a part of the base-up type spaces. So these are more general result and general setting, what it takes to be close range on these spaces. And you can see that this looks very similar to the first condition that Zurbuska had in terms of reverse correlation condition, right? So, they all involve this Neverland accounting function, which is something that you don't want to deal with. So, but what I was interested in, the observation they made. So Zurbuska made an observation that if it's close range on Bergman space, it's close range on the Hardy space, which is a subspace of the Bergman space. Then Aykroyd and Fulmer in 13, they showed something like this. If it's close range on this Bergman space, then it's close range on NP. So usually, like more often than not, most of the spaces like A2 is in A1. So these are so if you take P equals to 1 and N2, then you have that A2 alpha is in A1. And so it's another way to see that for a bigger space, if it's close range, then it's also close range on the smaller space. Then also, the Hardy space is a subspace of these spaces. And it's also, they also noticed one thing, Tijani in 14, they said like if it's close range on here, it's close range on the Hardy space. So there is some connection here. So it's a good thing to investigate. So in order to show that there is an implication like that, we're going to use something called absolutely monotonic function. Functions with whose can be represented as power series, with non-negative coefficient, and so real analytic functions, and which you can extend it to the disk and make it a complex analytic function. Any question? We are interested in A, 0, and 1 on the disk. So we define something. So all those weights we look at, 1 minus absolute z square, right? All those spaces, those weights are radial weights, okay? But they're not absolutely monotonic, increasing weight. So we define a Borel measurable function from the disk to the real line, positive real numbers. It's called an absolute monotonic radial weight on the disk if it only depends on the radial value, the distance of the z from the z from the cell, the center, right? And the way we generate this weight, we take an absolutely monotonic function on 0 and 1, and then we extend it to the disk, and it can be, and that there is a theorem which says that if you take an absolutely monotonic function which has non-negative coefficient, power series coefficients, you can extend it to the disk and make and get a nice complex analytic power series, and you can get a nice radial weight. So these are some examples of weights like this. So we had 1 minus z squared to the power alpha and all that, but that's not absolutely monotonic. But the reciprocal of that is. Here's some example. And we also sometimes the spaces. So we had this p we have been dealing with, hard disk by HP. It's not always 2. Sometimes you have mod z to the p and things like that. For how do you define that? Well, it turns out that weights like this, even if you take a pth power, they're still boundedly equivalent. Boundedly equivalent means that the ratio is bounded by positive constants below and above. So this is not much different. We can take a pth power of that and still do the things that we want to do here. There are spaces where you use the log one, but that's we don't use those spaces. The one that pretty much covers all of the spaces, most of the spaces that I talked about, initially gave you the list, is this one. And it can be shown that these are, if you take a pth power 1 minus xp to the power alpha, you take the ratio, and it's boundedly equivalent. And you can see that if you make the only problem is at 1, right? And you make the limit x goes to 1, it gives you a constant value there. Weights like this, those which are increasing really fast at a fast rate, we can find one. We can find one which is boundedly equivalent to WC. So it's not that bad, even if you have an like fast weight like that, which is increasing at a very high fast rate. Okay, so we have an assumption here. It's not a very big assumption. Mostly it's actually true on this basis. Sometimes not. So this is we know this as disk automorphism, this analytic self-map from the disk to the disk onto one to one and onto. This is a special type one. This one is its own inverse. So which we use the word involution, right? A function which is its own inverse. Which is a good thing, is that if it's bounded for on both spaces for this kind of map, then composition operator induced by, so it's bounded above and below, right? Because it's its own inverse. So it's closed range. So it takes the whole space to the space. And so it makes it kind of nuts that composition operator C sigma A is now closed range on both spaces because the inverse is the same one. And so it's bounded above, then it's bounded below. So why do we need that? Well, in general, the analytic self-map we talk about, phi, there's sometimes they map 0 to some value A, some A, or not always 0 to 0. So now we know we can use this kind of map to map the 0 to any point on the disk, and so we can take a composition, and we can switch the we can go to 0 to A, right? So we can just focus on maps which goes from 0 to 0, where phi maps the. So we focus on phi that goes 0 to 0. Because we can always, even if it goes to 0 to A, we can always composite with that and make it go to 0, right? So this assumption will help us to reduce to the case where phi just maps 0 to 0.
So this is bounds before simplified. You had like 1 plus phi of 0 over 1 minus phi of 0 earlier on.
Yeah. And we had this condition there, like for the theorem, yeah, phi 0 is 0. But the thing is, like you can, because it can be shown that it's bounded for the those automorphism. So. Right, so this is our first result. I mean, say, now we can go to the example after this. So what we're saying that we have two Banach spaces. One of them is a subspace of other, and we define a radial weight, an absolutely monotonic radial weight on this in one of the space. So what it does, it makes this one is a subspace of this, and the norms are related, and it just differ by this factor, WP, the weight. So what do we want to show that? So it's phi be an analytic self-map of D, and C phi maps the bigger space to bigger space, smaller space to smaller space, and if C phi, the composition operator, is bounded below on B, then it's bounded below on S. So initially I said, if it's bounded and 1 to 1, then closed range means it's just bounded below, right? So if it's bounded below on B, then it's bounded below on S, and we know it's 1 to 1. So if it's bounded on S and it's closed range on B, then it's closed range on S. Okay. So, but this boundedness condition, we have to have it. The reason is, most of the spaces is bounded, like HP and AP, but there are spaces where it's not bounded, so it's not a gift, as I said. So like spaces like Dirichlet space and certain base of type spaces where it's not bounded, so we have to have that condition there. So this is the proof of this theorem. So as I said, we can focus on the phi 0 to 0 case. We don't need to look at any arbitrary map, because we can always make it make 0 go to any A on the disk. So there's a classic lemma which you call a Schwarz's lemma, which says that if you have an analytic map on the disk and it's a bounded analytic function, the bound is less than or equal to 1, and phi 0 goes to 0, which is the assumption we have, then the modulus of phi c is less than or equal to modulus of c. So it's a very classic result, and for any of this map, there's a little part of the theorem that I omitted, so that we don't need. We just need this result. So we want to show that this norm on the smaller space is bounded below, right? So this is our definition of the norm. Now we know that this weight is an absolutely monotonic radial weight, so it has a power series representation with non-negative coefficients, and we can represent it this way. Now, well, we have the Schwarz's lemma. We can apply it here and get this inequality. Any question? Then there's, you can kind of do the permutation combination there, put it all together, and it looks like the norm on the bigger space. And we know that we have the assumption that it is close range on the bigger space. So that means it's bounded below with some delta, right? Well, once you have that, then then you can just go back to the, so it gives you the power series again with the weight for WP. It takes you back to the smaller space again. Yeah, there's not much trick. So it's the same delta. That's another. This is the I don't know how cool observation is that, but I think it's kind of cool that the delta that works for the bigger space, the same delta works for the smaller space. So it's bounded below. So here's an example. So those weighted Bargman space that I talked about for alpha less than beta, so these spaces are contained in these spaces, and so here's the norm on the bigger space, right? So, and if you use the weight this way, you get okay. Let me just. So if you take weight like this, and multiply the beta here, you get this weight for the smaller space, for the alpha, right? Cancel it out, and you only left with this part. So it's like a very simple implication that if it's close range on the bigger space, it's close range on the smaller space. And weights like this are absolutely monotonic. And and the good thing is, like, most of the spaces are covered by this absolutely monotonic weight. So they're not, as I'm not aware of, there are spaces where you can use weights different than this. So these are the spaces we work on, and it looks like it works for most of the spaces. So this works for spaces where you do not have the derivative involved, right? Some of the norms we saw this has derivative there. That is our next result. That will talk about, like, how does it work for the derivative. So another thing is we can take a sequence of weight, a sequence of absolutely monotonic radial weight, and we can do the same thing even if they change the setting using sequence of weight. We get the same result, as pretty much that. It's actually the same delta as well. So it works for those cases too. And one of the examples for the sequence cases, so is the if it's close range on the Bargman, then it's close range on the Hardy space. You can use weights like this, and and we know that weights like terms like this is actually which are convergent to the point mass at 1. Right. I think I have a little workout for that. So this is my HP norm, and I can change it since I know this term is which are convergent to unit mass. I can rewrite this norm this way, so I can see that connection between the norm in terms of the area measured with the sequence of weight. So, which once we have that absolute monotonic weight like this, we can use it to show that yes, it close range on the Bargmann space implies close rangeness on the Hardy space. So this is our second and last result, which is if you have the norm where you have the derivative involved, then you can do the same thing. It's just a different, it's few extra steps, but pretty much tells you the same result. If it's close range on the bigger space, then it's close range on the smaller space with the same setting, same monotonic radial weight, and everything. This time we have this extra f of 0 situation that doesn't give us much trouble since we know that. So first part is clear, we already used that. We know that it uses the p power on the real analytic weight. And we know that CP is linear. And so we can just, so what it says that, proving it, if it's bounded on the, for functions which take 0 to 0, it's also bounded on the spaces where it does not take 0 to 0. So I can just show this and still show it like for any general f, which is the same thing as here. Kind of like analogous result here, that you can, it doesn't matter where it goes, takes 0 to 0 or any other. And so it's just a fixed thing, right? Doesn't change much. I'll come to this one once I get it. So once again, same setting with the absolutely monotonic radial weight. Derivative, so you have the chain rule and everything to take it out. We know this absolute monotonic, so you apply the power series here and Schwarz's lemma, right? Then you can, so this part here is that you can take the sequence of function, which is the primitive or antiderivative of sequence like this, and fn0 is 0, it takes 0 to 0. And which takes us here. And which represent the norm in on the bigger space, and we know it's close range on the bigger space, so we use that delta here. Then again, once you write it up again, you see that you can bring that a in and represent that weight like we did the last time. And it's the same delta works for the bigger and smaller space. Alright, so this is these are the consequences from the theorem that now you can show that. So this bound, as I said, boundedness is not a gift here. So except Bargmann and Hardy other spaces, we have to mention that. It is bounded on these spaces, then it is close range on the bigger, then it's close range on the smaller. Here's an example of that. So we already showed that Bargmann and Hardy, you can show it in different, because those norm can be represented using the derivative of the function as well. So using the area measure on the disk. And you can show this again, if it's close range on the bigger space, then it's close range on the smaller space. It also works for sequence of weight. If you have a sequence of weight, the result still holds. And here's an example of that. This result, when I came up with this, when we came up with this, we didn't have an example for this. This is somehow, I think we sent the paper, then get the paper back for certain revisions, and then we realized, and you cannot add much. But it's like, oh, we had found an example, because we didn't know the existence of this space. There is a small space whose derivative is in the Hardy space. It turns out the sequence of weight, you can use it in this setting. You can say that you can use the same kind of weight here and show that this is also already a subspace and can be represented by weights like this. And you can show that this is if it's close range on the bigger space, then it's close range on the smaller space. And not sure if it's the most interesting space or not, because the composition operator on these small spaces, they do some nice things, and also certain things are not given. The boundedness is not easy. And also, another thing is, if it's bounded on this, then it's bounded on the bigger space as well. So there's an implication like this. So that's why I didn't assume boundedness on both. So if it's bounded on S2, it's bounded on D2. So if it's close range on D2, then it's close range on S2. Okay, so we had this this assumption we had that is bounded on both spaces for this special type of this automorphism, and the weight has to be a radial as well. The thing is, and this counterexample is actually shows that those are important assumptions that we have to have. Otherwise, the results don't hold. So if we take a weight like this, which is defined on the upper first quadrant. And so we define on that weight like this, and just on that part, the rest of the part is just one. So it's not radial, you can see that. Then you take the integrable, area integrable space functions which are area integrable, A1, and you define the smaller space with that weight. Okay, it can be shown that they are Banach spaces. You can, and the way you show it, I don't want to get into that detail. It just you use the if you use mean value theorem on sets on the disk, and you can show that this is bounded by the norm, and also there's a I think there's a function analysis part of it where if the point evaluations are bounded linear functionals, then you have Banach space, complete metric space. So these are Banach space which are given, and even if we don't prove it, we know back in our head these are like pretty much spaces that we actually talked about before, just in a different way we're using it here. So these are Banach spaces. We use a Mobius transformation, conformal map like this on the unit disk. So last time we had the map that we were talking about sigma A. That's the involution. That's the inverse of itself. This one is not. It's a little different, but it takes the disk to the disk, and the disk is also is in the pre-image as well. It can be shown that this part, this derivative of the inverse is bounded. There's a theorem. called limit like this. We know it takes to the 0 to I over 2, right? So we can find that bound easily from there. So one side is 3, another side is 1 over 3. And it also can be shown that this is also this ratio is also bounded. The weight, then we defined a made-up sequence, which is sequence like this, where you take the constant to be the 1 over the norm. So pretty much that sequence at norm 1, right? And functions like this, we know that this is not integrable with the measure mu that we defined, which kind of implies that this constant goes to 0 as k goes to infinity. We know that fk goes to 0 on this nice subset like this, which implies the composition also goes to 0 uniformly on the disk. And since this function, since f of g is in the area integral, not with respect to that weight, but it's area integral, so this norm has to go to 0. So now the part that we want to show that this is not bounded below. So we are on the U region and the rest of the U region, which is bounded by this norm on the disk, and then you have a change of variable here, and which you know already bounded by 3, and we know the so okay. So, and we know that the words are here. This composition. Let me go back. The different parts of it. So this composition goes to uniformly 0 on the disk on the U. So this goes to 0, and we already know this goes to 0. You know the derivative is bounded. So and we know the norm of this sequence is 1. So we can see that this is not bounded below. There's no such delta, right? So that's it on closed-rangeness. Do we have 5 minutes? If you have any question, I can do that. Because initially I said I'll talk about the compactness of this. So I also worked on the compactness as well. That's the first thing I worked on. This is the second problem. So this one is more interesting than closed-rangeness, I personally think, because it depends on the geometry of the image of phi. And so in short, so here's the disk and here's the image of phi. It all depends on the compactness of that operator, depends on the touch you have on the boundary. So if you have less touch, then it's compact. If you have more touch, then it's not compact. And there's a very, very, very fine line between that. How much touch you should have in order to be compact. And so the first result is about kind of similar to this. If the image is contained in a angular region. So if you have an angular region like this and your image is contained in that, you're good. You have a compact operator. That's the basic result. That's you can have. So that's what we started with. then we kind of, become more curious and try to go outside, and so how far can we go and still have compactness. So but this is not a few seconds thing. This is the biggest result in this field in terms of compactness, which talks about the essential norm, which is the distance from the space of compact operators in operator norm, says that this distance is given in terms of that Neverland accounting function, which is again something you don't want to deal with, but this is the first necessary and sufficient condition for this operator to be compact on this space, on the Hardy space. It's a beautifully written paper and nicely done, but using the most ugly function. So those are the region I'm talking about, Stokes region, where you get compactness, angular. So it's saying that if you have a univalent one-to-one analytic self-map of the disk, this is compact if and only if there is no angular derivative in the boundary. And that's one result without using those functions. And this kind of represent that derivative, right? This is the result we had in terms of, so there's a question posed by Donald Saracen. I don't know if you're familiar with the book of Saracen Complex Analysis. So he posed a question like, it's like, what is compact? How far can we go? And like, so there's bigger classes of compact. We had it was like, but his question was, are there operators where like in one touch point case, which touches the boundary at one point and still have compactness? What is that? So it works in a lot of other spaces if this norm goes to 0, but it's compact if it goes to 0. But for Hardy space, the basics, most classical space, it doesn't work that way. So if you have a multiple touch point of the image on the disk, you can make it go slow as possible. This thing can go to 0 and give you compactness. But for one touch point case, it's a bit sensitive, and then that gives rise to these conditions like this. So what we're trying to find a rate of convergence that will decide this. But instead of the rate, we found this. But it has to satisfy this condition. There is no particular rate. There's rate for certain classes of functions like this, but not a general rate that would decide this. That's all I have, and I'll move to questions.